if you discontinue to watch this video at one point, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I'm trying to learn electrical engineering today, the Maxwell's Corksrew rule and the Solenoid. And after we've done that, we're gonna do standing yoga. And if you participate in the standing yoga, then it's at your own risk. Maxwell's Corksrew rule. If one imagines a corkscrew being inserted into the wire in the direction in which a current is flowing, when the thumb will trace out the direction of lines of force, this is only one of various forms of rule connecting current and field direction, but it is probably the most widely used. So corkscrew. You have at first a corkscrew, you use it to open bottles sealed with a cork seal. That is made out of, we once did it in the past, in something, we did it in the past, now it is made out of the, I don't know what it's called, I forgot it, the part of the wood, of the layer of the outside of the wood, and you can put it into the bottle. And the corkscrew is now as a tool which is sharp at one end and you turn it into it, so it has a sharp end that gnaws into it, like a tooth that went to the side, and deeper end it's a spiral. And when you have a cork in it, you can pull it out. Now such a corkscrew is turning. Now what is now happening here with the turning? If one imagines a corkscrew being inserted into the wire in the direction in which the current is flowing, then the thumb will trace out the direction of lines of force. This is only one of various forms of rule connecting current and field directions, but it is probably the most widely used. Current coming out of page, current going into page. What do we want to tell us here? Do we mean that it's circular around them? The current is the electromagnetic field. And if you had a cork screw, you would go with it through it. You would grip on, you can't turn your arm around. So you would make a turn and then take it again, make a turn. Whatever, next thing, the solenoid. This name is given not entirely correctly to what is a long helical coil of wire. I don't know what helical is. Again, it is advisable for you to pass a current through such a coil in the laboratory and investigate the magnetic field around it using a compass needle. Okay, we're having some type of coil. A coil seems to be something where we're having some type of iron something coiled around it, and now we're having a coil. I don't know all these names. And when we're putting it under an electric current, and now a magnetic field arises around it. And a compass reacts onto it, because in the compass, the north path is the northern path of the needle goes to the magnetic field of the Earth. The Earth has in the north a magnetic field, and in the south or something like that. And the northern part of the needle searches for the northern part of the magnetic field. It's drawn to it. Is there actually so much magnetism that such tiny amount of iron notices the magnetic field? Okay, and the southern part is put to the south part. Your information should lead to the conclusion that a long helical current carrying coil has a magnetic field similar to that of a bar magnet. A bar magnet. The fields surrounding each small part of the wire used to form the coil join up to produce a concentration of lines of force running parallel to one another down the inside of the coil. We did it in physics, and there we had a little generator. I mean in physics, here in another series. And it was about how coal things work, and there was a generator, and the thing was, if you have a magnet turning inside of an iron coil, I think what what is a generator? The thing in the middle is turning, heated through a turbine or something. That's some water, coal, heat or something. So the thing's turning, and it turns now inside of a coil, which is magnetic, and having the non-magnet turning. And that friction with the magnetic field or whatever causes electricity to be generated. So that is a little background. I don't know how that exactly works. The fields surrounding each small part of the wires. The fields surrounding each small part of the wire used to form the coil join up to produce a concentration of lines of force running parallel to one another down the inside of the coil. The only lines of force outside the coil are those at the ends which fan out, as do the lines of force at the end of a bar magnet. The polarity of the ends of a solenoid can be remembered by using the following diagram. N view of coil with current flowing clockwise giving a south-seeking pole, N view of coil with current flowing anti-clockwise giving a north-seeking pole. So they said they could never cross. Is that the reason why they are on the inside? Or are they on the inside and outside? No, they said on the inside. The only lines of force outside the coil are those at the ends which fan out, as to the lines of force at the end of a bar magnet. Where the lines are got, the black thing is the current, and the force field are the magnetic fields, or the magnetic force fields. And the black thing is the wire, out of steel or something, or iron. And the current comes onto the wire. And the current runs around it. And the current runs on the wire around it. That causes a magnetic field inside of it. Why? Then why on the inside? And no, they go only to the outside, or they go to the outside. Because they cannot go around, because they are the other ones of the other one. That's what I think now. Okay, you will already know that iron is made permeable, I don't know what permeable means, to magnetic lines of force than air. That's more likely. So you can magnetize iron easier than air. It is easier for lines of force to pass through magnetic materials, to permeate them, than it is for these lines to pass through non-magnetic materials. Force passes easier to magnetic fields, or electromagnetic field. Magnetic force passes easier to magnetic fields. I'm thinking, does it somewhere help to make trains or something? I'm actually asking for how the trains works. This can be illustrated simply by using iron fillings to show the field existing between two unlike poles. And the alternation in the field when a piece of soft iron is placed between the poles. The lines of force crump into the piece of iron. Is the soft iron magnetic or non-magnetic? It is magnetic material. It is not magnetic, but it is magnetic material. I think that is what I mean. There is no magnet which can pull in air. Why? Imagine. I'm going to make a little mention of war. There are vacuum bombs. There are bombs which use up all the air in that area, and then actually there is no air to breathe in that area. For this reason, an electromagnet is usually provided with a soft iron core. So an electromagnetic is provided with a soft iron core. If you consider two such electromagnets, the electromagnet with a straight bar of soft iron as a core is not very efficient, as one of the two induced poles is not being put to use. If you consider two such electromagnets, I don't know what electromagnets, the electromagnet with a straight bar of soft iron as a core is not very efficient, as one of the two induced poles is not being put to use. Why are there two poles? From where to where goes the current? The magnet with a horseshoe iron core is able to create a closed magnetic circuit. We are on the other page. That is all the lines of force travel in either the core or the piece of material being lifted. So a closed magnetic circuit is that all the lines of force travel in either the core or the piece of material being lifted. That is a magnetic field. That is why we have a horseshoe magnetic. A horseshoe magnetic, now again, a horseshoe, we mean the horseshoes, and the horses, they have horseshoes, they look like that. And the horn of, it must grow like by humans. They're growing also basically out, and human nails were also bent a little bit to the outside. And by a horse, they are also bent a bit. No, I'm not completely sure about all that. I'm puzzling it a bit together. They are bent to the outside, and they are growing. Are they growing out of the foot? Or do they have just one toe? So I don't know what exactly is growing a bit. And the end of a horse has such a big nail now, and it's also like that. It goes to the side. Now it is able now. It is not possible to make a horseshoe onto it if that horse is walking a lot on hard materials like roads, on cement roads, because the horn is not hard enough for cement roads. And then there's a metal piece made onto that horn, and the horn has that size, so the metal piece is like that. It's such a thick metal piece that it's nailed into the nail, but it's nailed. It's dead material, so the horse doesn't feel it inside. It does not feel the pain in the nail. And so that is a horseshoe, and that is why these magnets always look like that. They're having that magnet, it looks like that, it comes down. They're having a coil around this magnetic field, and then it takes the magnetic material, which is not a magnet. So that is why we can take a car on the recycle whatever thing. The car is not a magnet. The car is not magnetic, but the car is magnetic material. So I'm looking into the wrong camera. So you can take such an electric thing, and then it takes the car, and now the electric field goes completely through the magnetic car, and then it has taken force on it, and now you can lift such a car up through the electric force field. You should note that the closed circuit is a magnet insofar as magnetic lines of force exist in it. But there are really no free poles, as at no point do the lines of force leave the magnet material to pass into the air. I don't understand that part, but it seems to be an important part whether these lines can pass into the air or not, because then it would make a pole, and then the car would be magnetized, then the car would work as a magnet. How far does the magnetic force reach if such a car is Many practical devices employ forms of electromagnets. Bells? Do they mean, because the next thing is buzzers, do they mean house bells? And buzzers, signals, galvanometers, and so on. I don't really understand a single of the examples, but I have my own one. The electric thing on the recycle bin, whatever recycle storage place. The construction of these devices and their use will form the subject of a later unit in this series. One present concern is to consider how the magnetic effect of a current can be employed as a basis for electrical measurements. So let's try to understand what our present concern is. It is to consider how this magnetic field of a current can be employed as a basis for electrical measurement. Because the electromagnetic field, because it's stronger, the more current we put on it. And we are able to measure how much electricity we're going to do. We are a bit obsessed with measuring the electricity amount, not so much with generating it, using it or something. We want just to measure it. Is it not a simple process? Whatever. We're going to continue with our big concern, how to measure how much electricity is there, in the next part. If you were here for electrical engineering, you can get directly to the next part of electrical engineering. If you stay here and participate in our 40-second yoga, then it's that your audience. Feet are standing together, we're breathing in the outside. Out and down. In and up. Out and down. In and up. Out, lean back, draw the shoulder blades together. In and up. Intertwine the fingers reach high. Without reach out front of the back. In and up. Intertwine the fingers reach high. Out, reach out front. in and up, out and back, up, out and back, in and up, out the arms down, in the arms up, out and down, in and up, hands together and hands down. That was very much on yoga. Thank you very much, and until next time.